Okay, so everyone, good afternoon. Okay, so sorry about the mix-up in the lectures and something, so I got a bit confused about who's doing what today. So in today's lecture, in today's session, we're going to continue on looking at, well, these are all really applications of the definition of the derivative. But we're applying the definition of the derivative to generate properties of the derivative. And the way I described this yesterday morning, was we have this kind of table of standard derivatives, or derivatives of a standard collection of functions, basic building block functions that we meet in our practice of mathematics. And we require to kind of assemble enough properties of the derivative that we'll be able to obtain derivatives of compound functions that are built up using the family of standard functions that are in the tables. Okay? So we need to know how the derivative behaves with respect to the various operations that are used to generate those compound functions out of the simpler building block functions. Okay? So we began that yesterday. We looked at proofs of the first two properties there in section 4.6. This was the linearity of the derivative. The derivative of a linear combination of functions is the corresponding linear combination of the individual derivatives. And then we also looked at the product rule, how the derivative behaves in relation to the operation of multiplying together functions. Okay. So today we're going to go on and look at a further two properties. The first one I'll just bring our attention to is theorem 4.8, which is the quotient rule. Okay, that follows on naturally enough after the product rule. The product rule dealt with products of functions. The quotient rule deals with quotients of functions. This is where we assemble a new function by taking a fraction, see there, u over v of functions. We want to know how the derivative of y relates to the two functions u and v and their derivatives. So this is this familiar rule, which most of you I'm sure have seen before, that if y is a quotient of functions u divided by v, then the derivative of y with respect to x, so understanding that both the functions u and v will both be functions of x, the derivative of y with respect to x is this expression here on the right-hand side, where we have the square of the function v at the bottom, evaluated at x, and on the top we have this mixture of derivatives, v times the derivative of u with respect to x minus u times the derivative of v with respect to x. So we can see that applied here. A couple of examples here. We'll just look at these. The first example where y is the expression x squared minus 1 over sine of x. Okay, so u is the numerator function x squared minus 1. V is the denominator function sine of x. So applying the rule there, we can read off the derivative of y with respect to x by making use of the quotient rule together with the derivatives of these standard functions. Okay? So we have a sine squared, a square of the sine function in the denominator, and then that mixture of derivatives in the numerator. Okay? So we have 2x times sine x. Okay? So 2x is the derivative of the numerator function times the sine of x, and then we have minus the original numerator, which is x squared minus 1, multiplied by the derivative of denominator function, which is cosine of x. Okay? So we get this expression here. It's complicated enough, but at least now we can see what the derivative of y is a compound function built up out of the simpler functions. And we got to that by making use of the quotient rule and the individual derivatives of u and v. Okay. Further example there, in number 2, this time we have y as a rational function, this quotient of polynomials, 2x minus 1 over 3x squared plus x. We can proceed to use the quotient rule to obtain the derivative of that function y. And you can kind of see how it's constructed here in this intermediate expression here, where we've got this long numerator. So we have the square of the original denominator, so 3x squared plus x, all of it squared. And then this combination on the top, you see the derivative of the numerator, 2x minus 1 is 2. That gets multiplied by the original denominator. Then we subtract the original numerator, 2x minus 1, times the derivative of the denominator, which is the 6x plus 1. Okay? And the only thing then to do is to tidy it up basically by simplifying the numerator and reducing that into standard polynomial form to get that final expression on the right-hand side. Now this is all very well as a rule, okay? And we can apply this rule and work with quotients of functions. But, you know, I don't just want you to proceed from here but believing in this rule because I told you about it, okay? What we need to do is verify or prove this rule for ourselves, okay? And see how it arises from the original limit definition of the derivative, okay? But rather than leap into it and prove it directly like we did with linearity and the product rule, instead, we're going to make use of this other property, which is called the chain rule. So before we come to proving the quotient rule, we're going to look at this chain rule. So we're going to make use of the chain rule to prove the quotient. Now, the chain rule refers to the other main operation we have, which we can perform on functions, and an extremely important fundamental operation, and that's the operation of composition, okay? Running one function after another, running one function on the output of another one, okay? It's fundamental across quite a lot of areas of mathematics. So again, a lot of you will have seen this before, but we're going to be proving it probably in our next lecture. So yeah, let's look at the statement of it. So here we've got the compound function y, this time expressed as a composition of the functions f and g. So y is f after g, f circled g. Okay, so you apply g first to the argument x, then you apply f to the result of that, and that gives you the value y of x. Okay. And there's a couple of different ways of writing this down. Using this first type of notation here, so we just make a kind of simplifying substitution. We substitute u for the value g of x, and so that we can then write y as f of u. And that gives us then our chain rule expression for the derivative of y with respect to x being dy du multiplied by du dx. So the derivative of y with respect to the variable u multiplied by the derivative of u with respect to x. Okay. You can see a couple of examples of it played out here. So we'll look at the first one where we have y equals x squared minus 1 all to the power of 5. Okay, so that's just a polynomial. It's going to be a polynomial of degree 10. And one approach could be to expand out that bracket, x squared minus 1 to the power of 5, to expand that out fully. Then you'd see y as a full, as a polynomial of degree 10, lots and lots of terms, and then just use the linearity principle to differentiate it term by term. But instead, we can save ourselves from doing that if we make use of the chain rule, okay? Because we see y made up of a composition of two functions. The inner function, which takes the argument x and calculates x squared minus 1, then the outer function, which raises that to the power of 5. So the outer function is raising to the power of 5. So we know what the derivative of that is going to be. Okay? So we can write down now the derivative of y with respect to x is going to be 5 times the bracket x squared minus 1 all to the power of 4. And using there the fact that the derivative of x to the power of 5 is 5 times x to the power of 4. But now the argument isn't just a single x, it's the x squared minus 1. So the derivative becomes 5 times the bracket x squared minus 1 all raised to the power of 4. But then we have to further multiply that by the derivative of the inner function. The inner function is the x squared minus 1, and its derivative is 2 times x. Okay? So this gets multiplied by the 5 times x squared minus 1 to the power of 4 gets multiplied by 2x. And all that's done then is to take the 5 times the 2x, and just bring those together at the front to write that as 10 times x. Okay. Another example in part 2 there is to differentiate y as the sine of 2x squared minus x. So there's an outer function, which is the sine function, and then the inner function is that polynomial 2x squared minus x. Very often the chain rule can be remembered as the kind of motto that to differentiate a compound function like that, built up using composition, you differentiate the outer function first. So the outer function here is the last function applied, and that's the sine. So you differentiate that first, it becomes a cosine of the original argument. It's a cosine of 2x squared minus x, and then that must be multiplied by the derivative of the next function in the sequence of compositions. The next function in the sequence of compositions is the inner function 2x squared minus x. And that has the derivative 4x minus 1. So the 4x minus 1 multiplies the cosine of the 2x squared minus x. So those are a couple of examples of operating the chain rule. There are further examples, but before we come back to talking about justifying the chain rule and the quotient rule, just to look a little bit further on in the notes there, you'll see there are some sections here on finding derivatives of inverse functions. We have this nice rule that the derivative of an inverse function is 1 over the reciprocal of the derivative of the original function. We've got a section here on finding slopes of tangents to parametric curves. Parametric curves in the plane is where you have curves defined by 2 separate functions. You've got one function for the x-coordinate of the points, another function for the y-coordinate of the points. And both those functions are in terms of a parameter. This is where the name parameterized curves come from. So here we've got a parameter t. You can think of that as a time-like variable. And as time proceeds from some starting value to some ending value, those coordinates x and y there will trace out a curve in the plane. And we can obtain the slopes of tangent lines to these curves by essentially applying the chain rule. Okay? And over the page there's a few examples. Well, they describe how that's going to look. Applying the chain rule to getting the derivative dy dt, let's say, and obtaining then the expression dy dx. See, dy dx is going to give you the gradient or the slope of the tangent line to the curves there. And there's a couple of examples worked out there. We've also got techniques of differentiation called implicit differentiation and logarithmic differentiation. And once again, these are both examples of applying the chain rule to different situations. Okay? So for the moment, I'll leave you to read through those after this and look through those examples. And then for the tutorials this week, if we go to the end of chapter exercises, this will open up questions. I think the questions 1 to 9 now will be available to us. So on page 56 there, all the way up to question 8. All the way up to question 8 there, we can see as applications of linearity, product rule, quotient rule, and chain rule. And then those further techniques of differentiation, implicit differentiation, and logarithmic differentiation, which are all more applications of the chain rule. Okay, so let's come back now to starting to justify these things, actually prove these things. Now we're going to focus first on the quotient rule. So I'm going to take them slightly out of order. So we're going to prove the quotient rule by making use of the chain rule. Now, I know I haven't proved the chain rule yet, but we're going to just assume it's true for the moment and make use of it to prove the quotient rule. Then afterwards, after we've done some preparation for it, probably next week, then we'll be in a position to prove the chain rule itself. Okay? So this is towards yep. So this is towards a proof of the quotient rule. Well, how we're going to prove this is when we see the expression y equal to u over v, the y is a quotient of functions, we're actually going to see this. First of all, we're going to split it off and write it explicitly as a product. Okay, so we're going to consider y as the product of u and 1 over v. And then we're going to see the 1 over v as a composition R of v. Okay, or you can think of this as u times the composition R after v, okay, where R is the reciprocal function. The reciprocal function defined by, well, the reciprocal function takes an argument x and it gives you the value 1 over x. Now, why am I messing around with things like that? Well, what that gives me is, when I'm considering a quotient of functions, I can now turn any quotient of functions into a product of functions and an application of the chain of composition as well. So I've got the product now of u multiplied by this other function. This other function happens to be the composition of the reciprocal function and the original denominator function v. So what we're first going to do now is first we will obtain the derivative of r. Now from the table we know that r prime of x is minus 1 over x squared. That's the derivative of the function 1 over x. We're going to prove that now shortly. So we'll obtain the derivative of r and then get the derivative of y by applying the product rule and chain rule. By applying this, namely the derivative of r, product rule, and the chain rule. Okay, so we're going to use the chain rule in combination with product rule, which we proved last time, and in combination with this result about the derivative of the reciprocal function, which we're going to prove first, right now. So then we'll have justified the quotient rule, assuming that the chain rule holds. The chain rule is the trickiest of the lot, so the chain rule we'll get to next time after doing some further preparation work later in this hour. Okay? So that's the plan of attack for the moment. Is everybody okay on seeing this, manipulation here? I'm going from a quotient of functions, getting an alternative view of that, seeing that as a product of functions, the numerator function u, but instead of the denominator function 1 over v, we're just thinking of that as the composition of r after v. Okay, so you apply v to x first, and then you apply the r, the reciprocal function, to that, and that gives you the 1 over v. Okay. So first we obtain the derivative of r. So here's the proof of r prime of x equals minus 1 over x squared. So we're going to prove this. We're going to apply the original limit definition of the derivative in order to get the proof of this. Okay? So by definition, now we have to stay away from x equals 0. This function isn't defined at this function isn't defined at 0. It's not defined at 0. It's not going to have a derivative at 0. So we apply the definition. We apply the definition for a point A not equal to 0. Any non-zero point A. And by definition, the derivative of R at A is defined to be the limit as x tends to A. Well, I'll just write down the definition first. Okay, should be familiar by now. The limiting value of the relative change in value of the function. The absolute change, Rx minus R of A, divided by the change that's going on with the argument. So I've somehow got to work this and show that it's going to be minus 1 over A squared. Okay, that's my goal. The goal is to get this equal to minus 1 over A squared. Because then I'll have demonstrated that the derivative of R evaluated at a point A is minus 1 over A squared. In other words, I'll have justified this formula for the derivative of R. So with this in mind, keep with this in mind that this is our goal to get this expression. We start to work with it. So the first thing to do is obviously to replace the expression R of x with what it's defined to be. So R of x is 1 over x, and R of A is 1 over A. Okay, so I get this expression here, putting in the definition of R. So somehow now I've got to work on this and get this expression when I take its limit to go to minus 1 over A squared. Now we can't take the limit immediately just by substituting the value x equals A, because we'll have a 0 on the bottom and we'll have a 0 in the numerator. 1 over A minus 1 over A. So we'll get this indeterminate form that we can't say what the value is. 0 over 0. So I must somehow deal with this obstruction. And, well, we deal with this obstruction because we will be able to get rid of this factor x minus A. Really, the x minus A isn't there, really. And you can see that by rewriting the numerator. Now, at the moment, we've got it as a difference of two fractions. The natural thing to do there will be to squash the fractions together. Write that difference of fractions as a single fraction. So we can do that if we put it over the common denominator x times A. So then the numerator is going to turn into A minus x. Okay. A minus x over x times A is equal to, as a single, that's a single fraction representation of the difference 1 over x minus 1 over x. Just using the rules for adding or subtracting symbolic fractions. But what we see now is, we see the same two copies of this factor. We've got x minus A on the bottom, and we've got the same factor, or minus it, A minus x. And A minus x is just minus x minus A. We've got the same factor on the top. So that can now be cancelled. So this is the limit as x approaches A of now just 1 over x times A, where we've cancelling the factor x minus A. Yeah, I can take it off the bottom, and I can take it off the numerator as well. Sorry, and this leaves behind a minus, because A minus x is equal to minus A minus x. Cancelling those two factors. There's no problem with dividing above and below by x minus A. It's never equal to 0. We're taking a limiting process, so x is never actually equal to A. This gets closer and closer to A. So this is a non-zero factor that we're cancelling out of the fraction. But now you can see where our result comes from. What's the limit of minus 1 over x times A as x gets closer and closer to A? Well, this fraction is just simply going to get closer and closer to minus 1 over A squared. Okay. So x is getting closer and closer to a, so the denominator is getting closer and closer to a squared. So I've reached my goal. So overall there we have that the derivative of r evaluated at a point A is minus 1 over a squared, which is exactly the familiar expression there for the derivative of the reciprocal function. Okay? So again, that's a nice application of the definition of the derivative. Okay? Doing it in the case of the reciprocal function. Is that okay then? Any clarification I can provide on that argument? Yes, question?
Do you need to prove this for the exam?
Conceivably, yeah, possibly. It could be, I mean, if you look over, I mean, I haven't asked these. No, if you look over the past few exam papers, you can see applications where I've asked you to from first principles, so working from the original limit definition to get the derivative of a polynomial term, x squared or x cubed or something. So, yeah, potentially, yeah, I could ask you to do the reciprocal function as well. Any other questions? Okay. See, because what you need to be able to do as mathematicians is, although practically, you know, when we're working on problems, we do make use of just all these standard results and properties. But as mathematicians, you really need to be able to, you know, rederive these expressions and understand where they come from, and fully derive, you know where all these results come from. So otherwise, we're just being engineers or so on, just blindly applying mathematical results. Okay, now, so what were we doing here? So this is interesting for itself. It's establishing the derivative of the reciprocal function. Remember, I'll be putting scans of all these pages up in the lecture recordings, as I do normally. But we wanted this. This was going to help us get to the quotient rule. So let's see how we can do that. So now we can do proof of the quotient rule. So the quotient rule, this is the form I'm going to use it, is that if y is a quotient u over v, this is going to imply that y prime, the derivative of y, is u prime v minus u prime v minus u v prime. This is the kind of notation. So we're just using this dash notation here for the derivative. So this is the quotient rule. Here in this notation. So we're going to see the proof of the quotient rule, but we're going to use now this trick here of rewriting the original quotient as a combination of a product and composition. So from before we have this y now not expressed as u divided by v, but now expressed as u multiplied by composition r after v. It's just another way of writing u divided by v. So you write it as u multiplied by the reciprocal applied after v. And we're going to take the derivative of this, y. Now the top level operation here is this multiplication. So I can take the derivative of this, I can apply the product rule. Because here I have a product of this function u multiplied by this bracket here. So using the product rule, this is going to be u, the derivative of u, multiplied by the function r composed with v, plus the function u multiplied with the derivative of r after v. What we see in this line is an application of the product rule. Okay, the derivative of this product is the derivative of the first factor times the second factor plus the first factor times the derivative of the second. So this here, we can write this now as u prime times 1 over v. R after v, remember, is representing 1 over v. Plus u multiplied, and now I want to take the derivative of this composition. So that's going to require me to use the chain rule. So using the chain rule on this is going to be the derivative of r applied to v, and then multiplied by the derivative of v. So what I did to get this line is I just rewrote r after v as 1 over v, and I've taken the derivative here of this composition. So that's using the chain. So I keep developing this. This is u prime times 1 over v plus u times, and now I'm going to make use of the result about the derivative of r. So we just proved that formula. The derivative of r is minus 1 over the argument of r squared. So this is going to be minus 1 over v squared, and this is still multiplied by the v prime. So there we've used the derivative of r. Now you see we've got this plus here, but we just want to bring this back into a single fraction now. Now what's the common denominator going to be? Well, on the left-hand side we've got a denominator of v. The term on the right we've got a denominator of v squared. So the common denominator will be v squared. So we've got u prime divided by v here, so to put it over v squared we'll need to have v times u prime. And here we've got minus u times v prime. Which, hey presto, is exactly the thing in the box that we were setting out to prove. Ooh, annoyingly, how about that? Reordered this product here. I've written v times u prime instead of u prime times v, but it's the same. Just those two functions multiplied together. So this is the quotient rule as required. So there we've seen yet another application of all these things, you know, all these different rules combined. So we'd already proved the product rule yesterday. We're assuming for the moment the chain rule. Proof of the chain rule is still yet to come, but assuming it's true for the moment. Separately, we proved the derivative of the reciprocal function. So those three things: product rule, derivative of the reciprocal, and the chain rule. Putting all those together implies the quotient rule. So this, well, presuming that we can prove the chain rule, then this is the proof of the quotient. Is that okay? Is there any questions about that? So this is why the quotient rule is true. This is why it has the form that it has. So you see it as a combination of product rule, reciprocal, and composition. This is how it comes out. Now, what we could do at this point is say, well, you know, this is great progress. All these results are, you know, succumbing to proof quite well. Without further ado, let's just steam on and try and prove the chain rule. So here's our first attempt to prove the chain rule. Just in the same way that we proved all the other things. Just taking the definition of the derivative as we have it at the moment and just trying to prove the chain rule. But I'm going to fail. So this is just to demonstrate that something else, something extra is needed, a new kind of angle or viewpoint is needed for the chain rule. So this is hopeless what I'm about to start. But, you know, we need to get an appreciation why it doesn't work and why we do need an extra kind of viewpoint. So suppose we have a function f as a composition of two functions, g after h. Okay? The chain rule says that the derivative of f at a is the derivative of g evaluated at h of a times the derivative of h at a. That's what the chain rule says. Well, let's try and prove it. So let's try to prove this. This meaning this chain rule. So in the same way that we've done for everything else, we say that the derivative of f at a is the limit as x approaches a of this familiar expression, f of x minus f of a over x minus a. On every occasion up to now, when we started with this definition and just kept at it a bit, we've gotten the desired result. So why not now? Okay. So the thing that we should do is put in the definition of f. So f is defined as g after h. So f of x will be g of h of x, and f of a will be g of h of a. Where are we going to go from here? When we did the proof of the product rule a few days ago, or yesterday, wasn't it? Let me just get the proof of the product rule up so you can see it, just to compare what we should do. It's coming up, yeah? That was the linearity. Proof of the product rule. So look, it started off exactly the same way. F prime a equals the limit of f of x minus f of a divided by x minus a. That was that line. Okay, so when we were doing the product rule here we had, here f was the product of these two functions. F was g multiplied by h. So the next line then was putting in f of x as g of x times h of x, and f of a as g of a times h of a. Then how did the proof go after that? Well, the proof worked by separating the g from the h. Separating the g from the h until we could see this expression here, this one down here, which was the derivative of g, and this one over here, which was the derivative of h. Then we could introduce those, and then we obtain the familiar product rule. Can I do a similar thing here? Can I separate the g and h's here? Well, it's hard to see how to do that from where we are now, because look, the h is buried inside of the function g as the argument to g here, and similarly over here, g of h of a. I need some way to break the h out of the g. So we've kind of hit a dead end at that point. Okay, so it's not clear how to proceed from here. So we need something new. We need something, a new kind of view, a new kind of angle on the definition of the derivative. Okay. So I'm trying to prove this in general. So I'm not dealing with any particular functions, g and h. I mean, if I knew what g and h were in particular, I could use their definitions here and maybe start to tease them apart. But I'm proving this in a lot of generality. So what is needed here? What is needed is a new angle on the definition of the derivative. Okay, so this is where we'll continue to be continued. This is where we'll continue from next time, having ground to a halt there and trying to prove the chain rule using the techniques which have worked for us so far up to now. We kind of see them fail here. Okay, so next week we'll return to the definition of the derivative. We'll get a little bit more out of it. We'll squeeze a little bit more out of it, so that we'll be able to prove this chain rule. Okay. So as I said, for the tutorials today, we can be working on those up to question 8 and the end of chapter exercises and exploring those. Okay. So I shall see you next Wednesday for this.